This episode is made possible by the Science Talks Trainings Vertical. Hello. Welcome to yet another smashing episode of Under the Microscope, where we spotlight materials and nanoscience. And through the science, of course, spotlight materials and nanoscientists. If you're new here, welcome to Under the Microscope. You have made the best decision to follow this podcast or subscribe to our YouTube channel, if that's what you're doing, if you're watching or if you're listening. So welcome to the thriving community of more than 10,000 people across social media platforms, all over social media platforms. If you're an oldie but a goodie, well, welcome back. Thank you for your continued support on all the different platforms that Under the Microscope is available on. Under the Microscope is the only podcast in the world focusing on materials and nanoscience, which is independent and also is in its 6th season, has more than 200 episodes featuring scientists from 20 different countries across the world. If you are new here, I told you, you made the best decision by following Under the Microscope on your podcast app or subscribing to the Science Talks YouTube channel. Let's talk about today's episodes. As the title says, is about next generation of particle accelerators. Now, you might know the particle accelerators, like the one at CERN or the one in Germany or a bunch of different ones. But there are only a few around the world because of the infrastructure that is needed and the cost in maintaining and building these kinds of particle accelerators. Today, we will learn what is the future of particle accelerators. And you would be surprised that the next generation of particle accelerators with lasers and plasma is to make these particle accelerators as compact as possible, as small as 3 centimeters. Now remember, 27 kilometers of the Large Hadron Collider in CERN and 3 centimeters, as we will discover today. And without compromising the quality of the experiments, the quality of the beam. That is the most important thing. So today's guest is going to tell us all about the next generation of particle accelerators and the opportunities that these sort of compact particle accelerators will generate for different fields of sciences, technology, and also in real life. Think about that, right? 3 centimeter, that's how big your particle accelerator can be without compromising the quality of your experiments. And of course, when you shrink the particle accelerator down, it also means that it is more affordable because it is cheaper to produce. All this and more we will learn in today's episode of Under the Microscope, episode number 220, Next Generation Particle Accelerators with Lasers and Plasma. Let's dive straight into it. A very quick word from our sponsor today. As you know, Under the Microscope is the flagship podcast of the Science Talk. In addition to creating innovative and engaging content, the Science Talk also offers science communication trainings. And one such training is Ace Your LinkedIn as a Scientist. This training is designed to teach you everything you need to know about acing your presence on LinkedIn. As a scientist, that is very, very important. As a scientist, this LinkedIn training will give you all the tools and tips to get started with your LinkedIn presence immediately. You'll get hands-on demonstration of the different features, profile optimization, hacking the algorithm, content crafting, engaging with your audience, and also growing your network on LinkedIn. So establishing your brand basically on LinkedIn as a scientist in that training that is called Ace Your LinkedIn as a Scientist. The next batch of Ace Your LinkedIn as a Scientist is in September 2024. More details are in the show notes or in the description, depending on where you're listening or watching. All right, on to today's episode. Hi, everyone. Welcome to Under the Microscope. I'm your host, Pranavti Chirsagar, and today we have with us Jens Osterhoff, who is a senior scientist and deputy director of the Bella Center at the Berkeley National Laboratory. Hi, Jens. How are you?
Hi, I'm doing fine.
Please explain your research to us in super simple words.
My research, or rather my team's research, is focused on making gigantic particle accelerators very small. So these accelerators they have, for example, at CERN, they are
Mhm.
among the largest machine they have on Earth, so many kilometers large to study the fundamental nature of physics, like fundamental particles that exist.
Okay.
And the problem with these accelerators is they're great for science, but they're quite expensive and very large. So what we are doing is we're trying to make these experiments or accelerators much smaller and consequently also quite a lot cheaper. And we're doing this by deploying a completely new particle acceleration technology that is based on high intensity lasers and plasma.
The ones, okay, wait, I have so many questions. Okay, you're creating miniaturized, I'm putting it in quotes, of course, particle accelerators with
Yeah.
lasers and plasma. Okay, perfect. And this is, of course, to bring down the cost without compromising the quality of the characterization. I'm assuming that is the case.
Yes, that's
Um,
correct. Yeah. But
so,
we've been doing new things that are not possible with these large scale machines. So, for example, since these particle accelerators are large, you can't do certain applications with them because they are so large. For example, it's very difficult to build them in a way that they are mobile, if you
Mhm.
wish.
Mhm.
And with our technology, at least in the long run, we're aiming at building mobile particle accelerators that you can also, for example, place on a truck or and then drive around and do things with them that are
In
not
the field.
stationary.
Oh.
In the field, for example, for field science, or there are also medical applications of these particle accelerators. And there are some applications you could envision, for example, nowadays you have particle accelerators in hospitals in wealthy countries, like for cancer therapy. And in the future, you could envision like not having them stationary in a hospital, but rather driving them around and, I don't know, go to less developed countries and then provide therapy there that is not available today. But there are many applications of particle accelerators nowadays that cannot be fully utilized because of the size of the machine.
You mentioned there are these miniaturized particle accelerators already in some hospitals. So
There are particle accelerators in hospitals that are based on traditional particle accelerator technology. And they are still large, too large to make them mobile, and they're expensive.
Mhm.
And my research aims at making these much smaller so that you can eventually apply them to, for example, cancer therapy maybe in a mobile platform even, or make these very large research infrastructures that are available only in one or two locations in the world much smaller, such that they can be installed more often than they are right now in the advanced research, or make other research infrastructures. They're called free electron lasers. These are very energetic photon sources. Again, they're quite big machines on the scale of a kilometer. And there are only a handful of those in the world today. We could make them much smaller with our technology. So this is the promise of this technology, why we're looking into it. It has a very diverse application spectrum,
Mhm.
and it can dramatically benefit several aspects of science, but also society.
I'm still stuck on the fact that there are these the large scale accelerators available to some of the hospitals. How these large scale accelerators, which are available, which are not these tabletop or mobile accelerators, not yet. What kind of applications do these have in hospitals other than the cancer therapy?
Cancer therapy is the main application, right? There are different types of accelerated cancer therapy in hospitals. There are
Oh.
very large therapy centers. For example, in Heidelberg in Germany, there's one for tumor therapy, but there are also accelerators for let's say surface tumors that are not quite as big, not quite as highly energetic, but
Mhm.
treat the surface tumor. And those all can be very much compactified in the future, we hope, with our research.
Oh, okay, okay. So it's like having, let's say, to take the example, because we are on under the microscope, taking an example, let's say, of an electron microscope, which was maybe 30 years ago, it would take the entire room and not very mobile. But now there are also companies who are doing, or there are also the tabletop scanning electron microscope available. The scale is not that small, like not comparable to the large scale accelerators to what your ambition is. But am I going in the right direction with this?
Maybe I can give you a concrete example in the sense that, for example, at Daisy in Germany, in Hamburg, there's a big research center in Hamburg for photon science, a place where I used to. They have an accelerator there, which is about 100 meters long and which provides electron of a particular energy. We measure this energy in giga electron volt. So this is an energy measure. And this accelerator is for a 1 giga electron volt beam, 300 meters long. And today we can achieve this sort of energy with our technology, like in an accelerator that's 3 centimeters long. Of course, there's a little bit of infrastructure around it, but this is the acceleration module in which the acceleration happens. So this is the kind of compactification I'm talking about, right? We're talking about orders of magnitude smaller without compromising the energy. And we are working toward also making the beam quality the same as from the large scale accelerators. This is where the current research focus is, to make them equally good. And in the future, then hopefully also surpassing the beam quality, which should be possible from the large scale machine. And you can imagine that this is something that cannot just make the machine more compact and also more affordable. Now you can imagine that with these supercomputers that fill the whole room, now that we have iPhone that have orders of magnitude more computational power than these large scale supercomputers they had 70 years ago or so. But you can use them for completely different things. Like because it's mobile and it has so much more computing power, you can do things with it that you couldn't before. And we expect something very similar with this new accelerator technology, so that we can, of course, do the same things that are done now on a large scale, on a much smaller scale, but we can also have new applications that benefit from the mobility, for example, of these systems in the future.
Oh, wow. You're absolutely right. Because right now, I cannot even think out of the box because in my head, an accelerator has the radius of, I don't know, several hundred or several tens of meters, depending on the intensity and the purpose.
Yeah.
But having it smaller I'm not able to even think about the different kinds of applications and the opportunities it will, like the doors it will open once we have these smaller sized or more compact or miniaturized, or what do you prefer? How should we call these accelerators that you're working on?
We call them compact usually, compact
Okay.
accelerator technology. Yeah.
Okay,
Or
compact.
laser plasma accelerators.
Okay, compact laser plasma accelerators. The possibilities would be endless, and it's amazing. And also with now the machine learning and all being used for the data analysis, because that is also like happening in parallel, right? Because that is another pain point or a challenge. Okay, you go to this beamline, you have, let's say, 3 full days of 24/7 just measurement, and you collect humongous amount of data. When we make the compact accelerators, and you make the compact accelerators, it would also be the data analysis aspect or data hygiene or management aspect. So are you also considering that, or are you mainly, or your group is mainly focusing on creating compact accelerators?
The team here at Berkeley Lab is working on these compact accelerators, but of course there's a whole supply chain, if you wish, around it, right?
Okay.
How do you collect data? How do you operate them? How do you optimize them? And you use the word machine learning in this context, and this is actually extremely relevant for what we're doing. Like we are using, for example, a machine learning based control systems to optimize these small accelerators such that they give us very similar beam properties every time we use them and optimize them to a very similar state.
Okay.
And then also, of course, the data that's being generated is then analyzed using various methods. And machine learning is definitely more and more a focus or a technique analysis method that we use.
Okay, that's brilliant. Last question around your research, and I promise we will move on with the questions. So last question about your research with this compact laser plasma accelerators. I see this also as a business opportunity, right? So how are you balancing that? Or is that something that you can share anything about this? And are you the only group then who is doing this? in the world, or like how is that landscape, the business
Yeah.
opportunity landscape in this case?
So I can say that first and foremost, of course, we are here in a research center in a national lab in the United States that being funded by taxpayers' money. We are developing technology for the purpose of society. And so our research, like to a large extent, focuses on making these large scale exploration machines, these particle colliders, much smaller and much more powerful using this technology. But of course, companies are interested in this. And we have worked with companies and are currently working with companies on application of this technology, that then, of course, the companies would like to monetize. Can't speak about everything we're doing. We are working, for example, with a company with the name of Tao Systems. It's a small startup company. They are developing miniature free electron lasers. This is essentially an X-ray laser that you can use to study materials and matter. There are many applications in biology, chemistry, pharmaceutical science, etc. And this company is trying to build very compact accelerators, and we are also trying to do that, and with the purpose of building a free electron laser for like many different applications. Our focus is probably more on the research side. The company has, of course, commercial intents, and we are working together on this. This is one example. So there are companies investing money into this technology already, but they still need national research laboratories at their side to do this research, because you need certain infrastructure that is expensive to start the development of this. So that's why I think we are great partners here with mutual benefit on both sides. And you asked about the worldwide landscape of this. So this is not the exact number, but there are about 50 groups or research teams in the world that are doing research on plasma-based particle accelerators. Our team here at Berkeley Lab is probably the strongest in the world, also in terms of numbers, in terms of group size. But it's certainly an activity that has been very quickly growing over the last year, also in particular in Europe. There's a lot of money now invested in Europe. This field was pioneered in the US initially about 20, 30 years ago. And since then it has been very rapidly developing. And now also since about 10 years or so, the investments in Europe are really catching up.
Okay. Thank you very much for being candid. And of course, I did not want you to name names of the companies. So I was just curious about the business landscape also, in terms of once the technology is ready to be scaled, you do need the production line, or you need to take care of the logistics side of things to produce these machines. And it's also good to know that there are other parts in the world where there is also research going on, and probably also their own business interest. This is, I think, the perfect example of academia, classic academia and industry working together to drive science forward, drive technology forward. Of course, you can do the research aspect of it, but when you have to think about the scalability aspect, then you do definitely probably also need the expertise from the business side, or from the industry. So I think this is a very good marriage, so to say. Would you agree with that?
Yeah, I agree with it. It's a good marriage also because there are different perspectives, of course, looking into the same problem. So we are maybe not as focused on making money
Commercialization.
with the commercialization.
Yeah.
And are rather focused on understanding the physics, controlling it well, delivering the technology with more of a general purpose, and the company is helping us to focus more into a product.
We are about to take a short break, but stay tuned, because when we return, we will dive deep into the career journey of our guest today. It is always inspiring to see the paths that lead scientists to where they are now. Don't miss it. I hope you're enjoying this episode of Under the Microscope. I'm your host, Pranati, and I absolutely love bringing you these conversations with the brilliant minds in the field of materials and nanoscience. It's incredible to hear about their research, their journeys, and their dreams for the future. At the Science Talk, through our flagship podcast that is Under the Microscope, our vision is very simple: We want to bridge the gap between the scientist and the public. We believe that platforms like this podcast can create a space where scientists can share their stories, challenge stereotypes, and inspire others with their passion and experiences. If you're enjoying these deep dives into the world of materials and nanoscience, I would love for you to consider supporting us by becoming a patron. Your support means the world to us. It helps us keep the podcast running, improve the quality, and reach even more curious minds such as you. As a patron, you will get some awesome perks like early access to the episodes, behind the scenes content, and even special shout outs on the show. Plus, you will be joining a wonderful community of science enthusiasts who believe in the power of sharing knowledge. So if you're up for it, head over to patreon.com/the science talk and see how you can get involved. Every little bit helps, and we are so grateful for your support. Thank you for being part of our mission to make science more accessible and engaging for everyone. Please follow the link in the description, in the show notes, on Spotify, or wherever you're listening to this or watching this on YouTube. And do consider being our patron. Thank you for listening. Thank you for watching. And let's get back to the episode. As I promised you, that was my last question around your research. I do have a lot more questions, but those I will save for later, maybe. I would like to know, and also it would be interesting for our followers and our listeners to know, how has your career journey been like, being now the deputy director at the Bella Center, right? That's what the acronym is, the Berkeley
Yeah.
Lab. How did this happen? Please walk us through your career journey to where you are today.
I started studying physics, I guess. That's where it started in, oh gosh, I think in 2000 in Würzburg in Franconia in Germany. I was there for 4 years. And then I moved to the University of Texas in Austin to the US to start graduate school there. Thought I would become a theoretical physicist at that time.
No.
I was very interested in some statistical mechanics. It sounds quite boring, but it's interesting, at least from my perspective. I tried to find a good thesis topic there in the field of nonlinear dynamics, statistical mechanics. And I couldn't find someone who also could pay my grad school tuition in theory, because typically there's less research funding in theory than there is in. So in the end, I found someone professor to supervise me, who also was willing to pay for the fee, for the grad school fee and a small salary. And that was in the field of high intensity laser plasma interaction. So that's how I really got into the field. And then I did a master's degree there. Then I had a chance to get a PhD position in Munich at LMU and the Max Planck Institute for Quantum Optics, where I worked for Ferenc Krauss, who just last year won the Nobel Prize. And we worked on laser-based particle acceleration in plasmas, so electron acceleration in plasmas. And this is where I stayed my whole career, essentially. Then I finished my PhD, did a little postdoc or half-year postdoc in a different group in Munich before I then actually went to Berkeley, to this place, to do a little more than 1 year postdoc. Then I got an offer for a tenure track position in Hamburg, in Germany, at DAISY, which I couldn't pass on, of course. Like, DAISY is a great place, and getting a career position or career track position in science is very hard to do. I was lucky there and accepted the job. And then I stayed at DAISY, and I essentially was the first person there who did research on laser-driven or plasma-based particle acceleration. And I built up a group there that grew over time, and some other groups were formed. And in the end, we had a quite strong team, and I stayed there until the end of the last year before they offered me a position over here at Berkeley Lab, which I couldn't resist to accept, because there's a fantastic team here. And so I moved back to Berkeley from Hamburg, and now I'm here still working on plasma-based particle acceleration.
So you basically, you basically had a tenured track position. That is like the dream of any scientist.
Yes, I had a tenure track position. I got a tenure track position at DAISY, which was then turned into a tenure position in 2013.
Right. And then you moved to Berkeley, and now are you going to come back to Hamburg, to DAISY?
you never know, but I'm planning to stay for the foreseeable future.
Okay, you don't want to move again? Why? Yeah, is it difficult to move? Intercontinental move? Is it? No, I'm kidding, of course. But no, that is brilliant. That is really interesting and also inspiring for the community of Under the Microscope, because we do have a lot of postdocs and PhD students or even master students who are majority of our listeners. So this is good information for them as well, that this is also a career path you could have. This is really cool. What do you miss about Germany? You spent a lot of time in Munich, spent a lot of time in Hamburg, in Würzburg, of course, and now you are close to San Francisco.
Some types of food, actually. The food in the Bay Area is great, but it's much more effort to get good bread, for example. And I like bread. So some food is great. I, of course, miss my parents are still living in Germany, so it's much more difficult to visit them. That's
Right.
something for family. And it sounds funny, but sometimes I miss the rain. We have essentially no rain from May until maybe October. And a rainy day now and then would be good.
Okay, do you want to switch places? Because as we are recording right now in July, it's raining. And we had like
Yes.
massive rain in the last few weeks. If you want to switch places, Jens, we can just switch. I can be near San Francisco and you can come and be in Manhattan. If you miss
For a day or two.
but I can imagine it's nice to have some rain in between, like some showers, just to cool down a bit the weather and change of scenery. Because yeah, otherwise it gets very dry. I totally understand. And yeah, bread, man. Maybe you can freeze the bread next time around and ask some of the bakeries to freeze the bread.
There's ways to get bread. It's just not as easy as in Germany, where you just walk a few hundred meters and then there's a bakery and you get
And like
the
fresh bread right there, fresh bread right there. Absolutely, absolutely. Perfect. You were coming back to the research now and
yeah.
not talking too much about bread, because this is breakfast time for you and soon it will be dinner time for me here. Würzburg, Munich, Hamburg, and at the Berkeley lab. It sounds to me that, and also it's quite interesting that you wanted to be a theoretical physicist and then you ended up doing, well, more on the experimental side of things, I would say. I'm pretty sure the theoretician in you is still thriving, but the more on the experimental side of things. And the next thing that I'm going to ask you, and I do get a lot of slack from my guests for asking this question, among all the research projects that you have been part of, if you have to pick one research project that you are super proud of, the one, okay, only one, could you pick one and explain it to us in simple words in the section that we call In Other Words?
Okay, it's easy. There's one I'm particularly proud of for sure. That project, it's a research project that I created and then proposed, got funded and conducted at Daisy while I was there. It has the name Flash Forward. It's a plasma-based acceleration project where we use very high quality particle beam to drive the accelerator in one of these small plasma structures. And I'm very proud of it because essentially poured 10 years of my life into it and created it. And in the end, it worked. Like we made a lot of interesting discoveries, advanced the technology quite significantly, had lots of publications from it. In that sense, it was, I'm particularly proud of that one. So what did we do there? So essentially, I mentioned earlier that these compact accelerators can deliver these very high energy beam over very short distances compared to conventional technology. And at this Flash Forward project, what we did there is we essentially took the next step and looked at how to improve the beam quality from these compact accelerators to match the quality that you can get nowadays from these large scale accelerators. And we made some significant advances there. And we showed how to, when you inject a beam, let's say a high quality beam from a traditional accelerator into one of these plasma structures to boost its energy, how to maintain the excellent beam quality of the beam that you put in, but then boost it, get the beam to much higher energy in this process. So this is what we did there. And then the other thing we did there is, for the very first time, we studied how to scale this plasma acceleration technology to much higher average powers. So nowadays, when you use these cells for acceleration, for example, with a laser, you can accelerate at a certain frequency. So you can accelerate maybe 10 bunches per second. This is pretty much the state of the art. And in Hamburg at the Flash Forward project, they have a very high repetition rate electron probe, which operates at up to megahertz repetition rate. So many orders of magnitude more than what is typically done in these plasma cells. And we could show and fundamentally study acceleration at these very high repetition rate, which is very crucially important for a certain number of applications that we would like to use this technology for in the future. So that was a big step. And I think this is one of the steps that not the research achievement that I'm most proud of. I could go into detail a lot now, but this will probably bore everyone on the podcast. And then we can discuss science offline.
I can understand why you chose this as the research project that is the closest to your heart, or the one that you're most proud of, because you were part of the entire process from inception to the results, which is in this case would be the publications, the multiple publications. That is brilliant. And also, of course, pushing the technology forward, which is, I guess, is like a crucial piece in creating these compact accelerators. This is like the piece. Yeah.
And the project is still ongoing, right? It didn't end just because I left. So it's still ongoing. They're still doing great research there, which is cool, right? And I really hope my successors, so Richard Darcy and John Wood, John is running the project now. They're doing an excellent job. And I hope they keep pumping out these research results and make sure the machine is working and progressing as it should, progressing the technology and that it should.
That is the best thing, right? As a scientist, because you're moving around quite a bit, but if you have introduced a particular field and now you see it flourish even after you have left, that there are successors, like you have left, that's your legacy, right? That you can, it must be also very nice and nostalgic for you to, whenever you come to Hamburg to visit the lab and being like, have some time with the machine and stuff.
Maybe. I haven't been back since I left, so.
Okay. You moved like a few months ago, right? You haven't been gone for that long, so.
Yeah, in January.
In January.
I moved to Berkeley in January.
Exactly. But this is wonderful. And I would love to know more about the science, and the science actually, what exactly that you mentioned, that the electron goes in and there is the plasma, and then the beam that comes out is like super. So just like, we don't have time probably to go into the entire science, because I feel like you can tell me so many stories and also explain the science for hours and hours. But if we were to, like, I would like to leave our listeners or watchers with some concrete sort of take-home message as to showcase the impact of this work, of this Fast Forward project that you were part of. So if we could do what is the intensity, or what is the energy of the electron beam that is going in probably, and then when it is going out from this plasma, after passing through this plasma, or any other way that we can imagine the impact in terms of numbers, that would be wonderful.
Okay. So for this Flash Forward project in particular, so we have a plasma cell that's a little bit longer than this one, probably 5 or 6 times as long. And you send an electron beam in that has been accelerated to 1 GeV over a distance of 100 meters. And then what we do in the cell, we
1
double
GeV, that is 1 giga electron volt, that is 10 to the power 9.
Yes, electron volt.
Electron volt,
essentially,
yeah.
So essentially an electron volt is if you take an electron, an electric charge, an electron, and accelerate it over this, within the voltage of 1 volt, right? It has 1 electron volt of energy. And the giga electron volt, as you said, is 10 to the 9 times that energy, and it's very close to the speed of light. To make you aware of that. So the particles that are accelerated are practically at the speed of light. And when you further accelerate them, it's essentially what happens is that their velocity doesn't grow anymore, but their mass essentially is increased. And so in Flash Forward, what we do is we take this 100-meter long accelerator, then we add, or what we did is we added this little cell at the end, and it doubled the energy of the incoming beam, like in a few centimeters. So you can, instead of using, again, 100 meters of conventional radio frequency technology, you use like 10 centimeters of plasma technology to essentially achieve the same result while maintaining its beam properties. And this is important in the case for Flash Forward for applications in these X-ray lasers. Berkeley Lab, we're trying to go even a step beyond that and try to use this technology to build the next generation or the next generation of particle colliders, where we're not talking about GeV, but TeV. So there's another 3 orders of magnitude higher.
That's the
Higher,
is it called tera electron volt?
Yes, it is tera electron volt. Exactly. This is where the particle colliders operate in this energy range.
Right. And because, because the velocity cannot go higher than, because it is already close to the velocity or the speed of light, then the mass is the one that is going up. And then in that case, your beam is more rigid.
So yeah, exactly. You have more energy stored in your beam. And then at TeVs, then you collide particle beams at TeVs, then you can study in these collisions the fundamental structure of matter, of the universe, fundamental particles. And this is what's done at CERN, for example, in the LHC. But the next generation of particle colliders will need to be even larger than what is currently operating at CERN. They have a 27-kilometer ring accelerator there.
Right.
You can imagine the next one, they're talking about a 100-kilometer accelerator now at CERN. And this is an expensive machine. So what we're looking into alternative technologies like plasma-based acceleration to make this next machine much more compact and affordable so that we can actually go this step and further explore the universe.
That is so cool.
And all the structure of matter.
That is so cool. Yeah, sorry, go on. I just have to, okay. I said we don't have time, but I'm just going in and let's just go for it.
You can cut just whatever you like.
No, I won't. This is amazing.
And then on the other hand, you have these other extremes. So this is the largest scale. But on the other hand, we're also working on, I mentioned therapy. And there are ideas, for example, that you can make these particle accelerators so small, like much smaller even than what I have in my hand right now, rather like a millimeter or smaller, such that you can install them at the tip of a fiber. And so you have something like, if you wish, an endoscopic particle accelerator that you can insert into a patient, accelerate particles right where they are needed, for example, inside a tumor, and then do therapy right there. You have some sort of an endoscopic instrument with which you can do tumor therapy. This is another dream, if you wish, at the other extreme.
But oh my God, this field is so big. Okay. So for the cancer therapy or for the tumor therapy, to burn off this tumor or get rid of this tumor or whatsoever, don't we do that already with the technology that we have? Or
yes and no. Yes, there are machines that can do particle therapy or cancer therapy with particle beams, but they are, as I said, expensive. And they are expensive and large, and many countries just can't afford them. If you look into like where these therapy centers are, they're always in the wealthiest countries in the world.
True.
Now, and then there are other techniques to destroy cancer, for example, that are maybe not as advanced as particle accelerators, but they rely on radioactive materials. So essentially, you bring a little bit of radioactive material into the tumor, and the radioactive material destroys the tumor. It also exists. But again, this is something that is not done in the developing countries in the world, because there are very often export controls for radioactive materials, so that you can't do it there. So what we really need is an affordable particle accelerator technology where there's no export control consideration, that is affordable enough so that you can go to Africa and treat cancer there. And this would have an immediate impact, and it just would save a lot of lives, right?
Yeah.
So in that sense, you have this technology to, of course, do science on one end, and many people question, of course, the societal need do that. I think I'm fully supportive, right? We need to do fundamental science, but we also need to look into society or issues of society, into making sure the technology we're developing is feeding back into improving our society immediately. And
Yeah.
for example, cancer therapy in developing countries where this is not broadly available is certainly a big motivator also to work on this technology, because there's so many possibilities
Yeah.
to contribute.
You're absolutely right. And this is another aspect I have to say. I'm very happy that we have you here under the microscope. Earlier, I highlighted that you are at the interface of academia and the industry to make sure that there is the technological advancements, so to say, but now also adding the societal aspects. I'm very happy to have you on under the microscope. And I feel like I need to do like a series of episodes with you to go into the details of the technology and the science itself, because I think this is really fascinating. And this is also really cool, right? Because it's not just the compact accelerators, but you're also thinking about like really miniaturized particle accelerators or electron accelerators, sorry, which can be on the tip of your atomic force microscopy tip, probably to that extent ish. No,
It's well, if you do an
endoscopy.
what's the word? Endoscopy. If
Yeah.
someone looked into your knee to study how your ligaments are, right?
Yeah.
You can imagine a similar device that you could insert just with a particle accelerator at the tip, not with a camera or with an optical loop.
This is brilliant. And I'm serious about having you back again on under the microscope or doing just like series of like accelerators and all the possibilities and what is happening with you. So it's very clear to me, Jens, that the research aspect of being a scientist is really exciting for you. What else do you like about being a scientist? Because doing the research itself is, of course, rewarding, but what else do you like about your life as a scientist? Tell us.
First of all, it's always busy. There's always stuff to do. And scientists are usually intrinsically motivated, so they always find cool stuff to do. Every day, I think it's the diversity. It's the best part of it. So there are no 2 days like another, usually, as a scientist. So there's something new every day. And you work with very diverse, very intelligent people every day, which is fantastic. Some of them are very interesting, just very enjoyable. And then, of course, there's the motivational aspect that you already mentioned, that, of course, doing science is fun. You can discover things in nature that maybe no one has discovered before, and then develop technologies or methods that are very useful for society, and you can make an impact. I think that's what's motivating me and what's keeping me motivated every day.
And that is brilliant. So it sounds to me, Jens, that your research experience so far has been wonderful. And I hope it will continue to be wonderful. I've only been talking to you for 1 hour, and I probably got the highlight reel of your life as a scientist. But if you had 3 wishes to improve your research experience, what would you ask for? And I'm not promising anything here, okay?
Unfortunately not. But of course, as I mentioned, right, there's always things to do. So there's never enough time, in other words. So if I had more time, that would be fantastic. And in particular, balancing, of course, the job with family, etc., is sometimes difficult. So in that sense, more time would be fantastic, but that's impossible. So the other thing, of course, that always helps is more funding. Maybe you can help with that. Research funding, of course, is great. And then you have to pick the right project. And yeah, just continue to pick the right projects that are realistic, that lead to something, is something that I wish I will do. But other than that, I'm very happy. So I don't have any big requests. Just money, time, and wisdom.
Money, time, and wisdom. So easy, of course. I can just use my magic wand to be like, yeah, of course. You can have more time, more funding, and more wisdom to choose and have the foresight, as you mentioned, like what is going to work in the future. Let me learn already from the mistakes that I might make in the future and already tweak my approach in the present. Very realistic wishes, in a way, especially if I think about it, you are going to give the gift of time and funding to the next generation of scientists, right? When you're the technology that you're working on with the compact accelerators, that will save next generation of researchers a lot of time and funding, because then they don't have to apply for the beamline and go there. In a way, you're like paying forward. What was it? Fast forward was their project name.
Flash forward. Yeah.
Flash forward. Yes, exactly. But no, this has been great, Jens, and I see that we are over time, and I see that you have to go. One last question before I let you go. One last question. Every guest of Under the Microscope also gets to take over the Real Scientist Nano Twitter account or X account for one entire week, which has more than 3,000 followers. And you will soon be taking over the account, the Real Scientist Nano Twitter account. So what can the followers of this account expect in the week that you will be tweeting from this account?
Yeah, that will be during the week of our most important workshop, the Advanced Accelerator Concept Workshop, which will happen in, I think, the third or fourth week of
Third week.
July. Third
Yeah,
week,
oh,
thank
fourth.
you. In
Fourth, yeah.
Naperville near Chicago. And I will be tweeting from that conference and hopefully showcase some of the amazing people that work in the field of science and show the great projects they're working on. And myself, I will learn a lot at the conference, but usually where the latest and greatest advances are being displayed, and maybe even for the first time. And so we will learn some news there, and it should be exciting. Should be an exciting week.
That sounds wonderful. So we will be attending this workshop with you. And so we also get the experience of attending a conference or a workshop and how hectic and fun and exciting it is. And I do expect also a lot of pictures of the conference venue. I'm assuming this will be a beautiful place. I hope you will have good weather. Maybe not so much rain. Let's see.
No, I don't know. It may be even terribly hot in Chicago. I don't know.
I hope then you get some rain just before the conference week, so that when you arrive there, it's not super duper hot. This is brilliant. I look forward to having you, of course, on Real Scientist Nano, attending the conference with you virtually, and meeting a lot of amazing folks in the field of advanced accelerator concepts. So looking forward to that for sure. Thank you very much for your time, Jens. I learned a lot. This was an amazing experience, and I am serious about having you back on Under the Microscope or any other content format on the Science Talk. So thank you very much for your time.
Thank you. It was a great pleasure.